The story of the sonar system begins in the depths of human curiosity and ingenuity, tracing its origins back to the early attempts to understand and interact with the underwater world. The idea of detecting objects underwater was not new. Sailors and mariners had long been fascinated by the mysterious depths of the oceans. The development of sonar, however, was propelled by necessity, innovation, and the evolving needs of exploration and warfare. In the 19th century, with the advent of industrialization and the rise of submarine navigation, the challenge of underwater communication and detection became more pressing. Please subscribe my YouTube channel and press the bell icon for new update. The first recorded attempts to develop an underwater detection system came in the early 1820s, when Daniel Colladon, a Swiss physicist, conducted experiments in Lake Geneva to measure the speed of sound in water. Colladon used a submerged bell and a listening device to study how sound waves traveled through the medium. While his work was primarily scientific, it laid the groundwork for future technologies. By the late 19th century, interest in underwater acoustics had grown, fueled by advances in physics and the growing strategic importance of naval power. However, it was not until the early 20th century that the first practical applications of underwater sound detection emerged. The sinking of the Arms Titanic in 1912 highlighted the dangers of underwater icebergs and spurred interest in developing technologies to detect submerged obstacles. This tragedy motivated inventors like Reginald Fessenden, a Canadian physicist, to create the Fessenden oscillator in 1914, a device that could emit and receive underwater sound waves. Although its range was limited, it marked the birth of active sonar technology. World War I provided the impetus for further advancements in sonar technology. Submarine warfare, particularly by German U-boats, posed a significant threat to Allied naval forces. To counter this, researchers and engineers worked tirelessly to develop systems capable of detecting these stealthy underwater vessels. The term ASTIC, an acronym for Anti-Submarine Detection Investigation Committee, was coined during this time and referred to the first operational sonar systems developed by the British. These early systems used piezoelectric crystals to generate and detect sound waves, enabling the detection of submarines at close range. Despite its promise, early sonar technology was rudimentary and faced significant limitations. Detection ranges were short, and interpreting the data required skilled operators. Nevertheless, these early systems represented a crucial step forward in the development of sonar as a military tool. By the end of World War I, sonar had established itself as an indispensable component of naval warfare. The interwar years saw steady progress in sonar technology. Advances in electronics and materials science allowed for the development of more sensitive transducers and improved signal processing techniques. By the outbreak of World War II, sonar had become a critical element of anti-submarine warfare. The Allies, particularly the United States and the United Kingdom, invested heavily in sonar research, resulting in significant improvements in detection range and accuracy. During World War II, sonar played a pivotal role in the Battle of the Atlantic, where Allied convoys faced relentless attacks from German U-boats. Improved sonar systems, combined with coordinated tactics and the use of depth charges, helped turn the tide in favor of the Allies. Sonar-equipped ships and aircraft became the primary tools for hunting submarines, significantly reducing their effectiveness and ensuring the safety of vital supply routes. Post-war developments in sonar technology were driven by the Cold War and the accompanying arms race between the United States and the Soviet Union. The advent of nuclear-powered submarines, capable of remaining submerged for extended periods, posed new challenges for sonar systems. To address this, researchers focused on developing low-frequency sonar systems capable of detecting submarines at greater distances. The introduction of passive sonar, which relied on listening for the sounds emitted by submarines rather than actively sending out sound waves, further enhanced detection capabilities. The 20th century also saw the diversification of sonar applications beyond military use. The development of commercial and scientific sonar systems opened new frontiers in oceanography, fisheries management, and underwater exploration. Echo sounders, a type of sonar, became essential tools for mapping the seafloor, enabling the creation of detailed bathymetric charts. These charts proved invaluable for navigation, resource exploration, and environmental monitoring. In modern times, sonar systems have reached an extraordinary level of sophistication. Military sonar remains a cornerstone of naval strategy, used for anti-submarine warfare, mine detection, and underwater communication. Advanced sonar systems such as towed arrays and hull-mounted arrays provide unparalleled detection and tracking capabilities. Submarines, equipped with sophisticated sonar suites, can operate stealthily while maintaining awareness of their surroundings. Autonomous underwater vehicles, AVs, and remotely operated vehicles, ROVs, also rely on sonar for navigation and data collection. Beyond the military domain, sonar has become an indispensable tool in various civilian applications. Marine biologists use sonar to study aquatic life, tracking the movements of fish and marine mammals. Commercial fisheries employ sonar to locate schools of fish, optimizing harvests while minimizing environmental impact. In archaeology, sonar aids in the discovery and mapping of submerged ruins and shipwrecks, shedding light on human history hidden beneath the waves. Environmental monitoring is another critical application of sonar. Researchers use sonar to study ocean currents, monitor underwater volcanic activity, and track changes in the seafloor. These efforts contribute to our understanding of climate change and its impact on marine ecosystems. Seismologists also use sonar to detect underwater earthquakes and tsunamis, providing early warnings that can save lives and reduce damage. Sonar technology has even found its way into everyday life. Recreational boaters use fish finders, a type of sonar, to locate fish and navigate safely in shallow waters. Divers and underwater photographers rely on handheld sonar devices to explore unfamiliar environments. These consumer-grade systems, though less advanced than their military and scientific counterparts, demonstrate the versatility and accessibility of sonar technology. One of the most exciting developments in sonar technology is its integration with artificial intelligence, AI, and machine learning. Modern sonar systems can process vast amounts of data in real time, identifying and classifying objects with remarkable accuracy. Algorithms enhance the ability to detect subtle signals in noisy environments, enabling the identification of elusive targets such as stealth submarines or rare marine species. These advancements have transformed sonar into a powerful tool for both defense and discovery. Despite its many benefits, sonar technology is not without controversy. The use of high-intensity sonar in military and commercial operations has raised concerns about its impact on marine life. Studies have shown that some marine mammals, such as whales and dolphins, are sensitive to sonar frequencies and may experience disorientation or physical harm when exposed to intense sound waves. This has led to calls for stricter regulations and the development of eco-friendly sonar systems that minimize harm to marine ecosystems. The future of sonar technology holds immense promise. As humanity continues to explore and exploit the oceans, the demand for advanced sonar systems will only grow. Emerging technologies such as quantum acoustics and bio-inspired sonar are pushing the boundaries of what is possible. Quantum acoustics, for instance, could enable the development of sonar systems with unprecedented sensitivity and resolution, capable of detecting objects at extreme depths and distances. Bio-inspired sonar, modeled after the echolocation abilities of bats and dolphins, offers the potential for highly efficient and adaptable systems that mimic the natural world. In addition to technological advancements, the increasing integration of sonar with other sensing modalities, such as LiDAR and radar, is creating multispectral systems that provide a more comprehensive understanding of underwater environments. These hybrid systems have applications ranging from autonomous navigation to underwater construction and disaster response. The story of sonar is one of continuous innovation and adaptation, driven by the human desire to explore, understand, and protect the underwater world. From its humble beginnings as a scientific curiosity to its current status as a cornerstone of modern technology, sonar has profoundly shaped our relationship with the oceans. As we look to the future, the potential of sonar to unlock new frontiers and address pressing global challenges is both inspiring and limitless.